Let's vary the magnetic flux now through the small solenoid by changing the distance, how far off center the two solenoids are. So to do that, I'll make them flush here. I have a ruler to give us a x-axis, an independent variable. I'll start with the small solenoid a couple centimeters, 2 centimeters out from even touching the larger solenoid, and then I'll end with them completely flush, centered. So the number that we're going to record is this number here, starting at 18 centimeters is with the two solenoids not overlapping at all, and then 0 centimeters will be completely overlapping. Okay, so let's take some measurements here. Is this thing okay? Whoop. Oh, wow. Totally lost my signal. Press auto set. Very strange. So it auto sets them with a nice scale and moves them so that the two signals are not overlapping, but I'm going to move them back down to around 0 offset. Something like that. And let's measure. So now channel 1 is set to 10 millivolts per division. We have 1. So that means that channel 1 has a smaller current going through it than we had measured before. So let's measure that again with the cursors. We want them on channel 1, not channel 2. Yes, so cursor. Move the top one down and move the bottom one up. And now we're seeing only 32.5 milliamps in the large solenoid. But everything's the same. Wonder why it changed. Didn't touch the function generator. Well, that'll have to work. So 32 milliamps through the large solenoid. And 18 centimeters from being completely overlapped gives us what EMF across the small solenoid. So let's measure on channel 2, the blue channel, which is measuring the voltage here. So go to cursor, and this is a different scale. This is on 50 millivolts per division. So if I move the cursors to the trough and press select to get the other one, and peaks of this sine wave, I see I have an EMF of 131 millivolts. So for 18 centimeters, we have 131 millivolts induced. Now I will reduce the separation by 1 centimeter, make sure they're still aligned axially, and remeasure the EMF. So at 17 centimeters, we have 166 millivolts induced on the small solenoid. And then I'll move them so they're just touching. which means 16 centimeters, and remeasure. So this is the first data set. The first variable we've chosen being distance here of the two solenoids. So for 16 centimeters, we show 232 millivolts induced across the small coil. And now move it another centimeter so that they're partially overlapping. 15 centimeters. And the number here, delta, says 310 millivolts. 14 centimeters from being perfectly centered. Now the channel 2 signal has gone off the scale, so I'll reduce the volts per division, turning this knob this way once. Okay, now we're at 100 millivolts per division. So I'll bring the cursors back to align with the signal here. 441 millivolts at 14 centimeters. 13. We have 610 millivolts. 12 centimeters. Reduce the volts per division again. Move the cursors. "12 centimeters, we have 793 millivolts. 11 centimeters. "983 millivolts. 10 centimeters separation. We have 1.21 volts. Turn down the volts per division again. And go to 9 centimeters. And adjust the cursors. .48 volts at 8 centimeters. .68 volts, 7 centimeters. .92 volts at 6 centimeters. .12 volts at 5 centimeters. 2.32 volts at 4 centimeters. 2.54 volts, 3 centimeters. Will give us, oops, 2.73 volts, 2 centimeters. .93 volts, 1 centimeter. 3.03 volts, and then 0 centimeters, completely, 2 solenoids are flush, centered. We have 3.10 volts. Next, we'll adjust the frequency and see how that affects the EMF.